So today's lesson is going to be on heat. And let's go back to this heating curve that we looked at in Unit 7, where temperature is our y-axis in degrees Celsius, and heat energy is going to be our x-axis. And again, you may see this as time. Physicists like to look at things in terms of time, but in chemistry, we care about the heat energy. And if it's the heating curve, it's going to have a structure that looks like this. And we know here is our solid, our liquid, and our gas. And if this is of water, we know the temperature at which water goes from a solid to a liquid, or a liquid to a solid, is 0 degrees Celsius. And the temperature at which it goes from a liquid to a gas, or a gas to a liquid, we know that is going to be 100 degrees Celsius. And we learned that during our phase change, the temperature is staying the same. The heat energy is actually increasing, and that heat is being used to break those intermolecular forces that are holding our substance together as a solid. And the same thing holds true as our phase change from a liquid to a gas. Our temperature remains constant. The heat energy does increase. Those final remaining intermolecular forces are being broken to put the substance into its gaseous form. So we can take this heating curve that we've looked at, and we can go one step further, and we can do some mathematical calculations in terms of heat. All right, so for our solid, our liquid, and our gas, we are going to use the same formula, Q equals mc sub P delta T. Where Q is defined as the heat gained or released by a substance. And this is going to be measured in joules. M is our mass of a substance, which we know mass is in grams. C sub P is going to be the specific heat. And that's actually two words. Need to make that look a little neater for you. Specific heat. And this is defined as the amount of energy needed and this energy is going to be needed to raise the temperature of 1 gram of substance by 1 degree Celsius. Now, different substances have different specific heats. You will notice on your reference tables on page 1, the specific heat of a number of different substances are provided for you. The units are joules divided by gram degrees Celsius, and this makes sense because heat is measured in joules, and specific heat is the amount of energy needed for 1 gram of substance to change its temperature by 1 degree Celsius. So there's our grams and our degrees Celsius. And delta T is the change in temperature. And delta T is calculated by doing the final temperature minus the initial temperature. So TF minus TI. Now, during our phase change, Q is going to equal M, heat of fusion, where the heat of fusion of water is on your reference table. All right, and that's going to be 334 joules per gram. Notice there's no degrees Celsius here because there's no change in temperature. All right, so this is still the amount of energy needed for the phase change. For our phase change from a liquid to a gas, this is Q equals M, heat of vaporization. And I remember that this heat of vaporization is from a liquid to a gas because we do know the process of going from a liquid to a gas is called vaporization. And your heat of vaporization for water is also defined for you on your reference tables. And you'll notice the specific heat of water for ice is 2.05. For steam, that's its gaseous form, it's 2.02. And for a liquid, it is 4.18. So water, depending on which phase it is in, has a different specific heat. So let's do some practice problems with this information. How much heat is absorbed when 20 grams of steam increases its temperature from 250 to 270 degrees Celsius? So 250 is a gas, and I'm going to 270, which is a gas. All right, so I'm starting as a gas, and I am ending in its gaseous phase. So this is a one-step problem. Q equals M, C sub P delta T. Where my mass is 20 grams. My specific heat of water in its steam form is 2.02 joules per gram degrees Celsius. And my change in temperature, final temperature is 270 minus initial temperature, which is 250. And so when I plug this into my calculator, I find that I have a change in temperature, or I'm not a change in temperature, excuse me, a change in heat. The absorption of heat is 808 joules. You'll notice this is a positive value. All right, and remember in chemistry, the positive and the negative do not give us the magnitude of the value. It tells us whether something has been absorbed or released, and in this case, we're talking about heat. So the absorption of heat is positive. How much heat is released when 10 grams of water drops in temperature from 210 to 10 degrees Celsius? So here we go. Now I am releasing. So if positive is absorbing, releasing is going to be a negative value. So this is a way that you're able to check your work. All right, if something is being absorbed, you should get a positive. It's being released, you need a negative value. So if you don't get a negative value, you know you've done something incorrect. So we are going from 210. So 210 is a gas, and I am ending at 10 degrees Celsius. 10 degrees Celsius. And let's just make this 210. All right, so I'm going from a gas down to a liquid. So if I start as a gas, this is a 1, 2, 3 step problem. 3 steps. I'm at a gas, then I condense, and now I'm a liquid, and I continue to lose heat. So 3 steps. So let's start with my Q1. My first Q is my gas. Q equals MC sub P delta T. Where my M is 10 grams. And my specific heat for steam is, again, going to be 2.02 grams or joules per gram degree Celsius. Now, my change in temperature. Here's where students mess up, all right? And it's right here at this point, the change in temperature. I started at 210. My gaseous temperature ends at what? 100. This is my change in temperature. I start at 210 and I end at 100 degrees Celsius. Now, yes, my final temperature is 10, but this is a three-step problem. My gaseous temperature ends at 100. So when I plug that into my calculator, I find my first Q is negative 2222 joules. Now, we are not rounding to the rule of 3. The rule of 3 is the final thing we do at the very end of the problem, not while we're creating work. So what is my second Q? So if I come back here, my second Q, I'm now at this gaseous form, all right? I am going to condense. So that is Q equals M, heat of vaporization, where my mass is still 10 grams, but my heat of vaporization for water is going to be 2260 joules per gram. Now, I am releasing heat. So what do I know about my value here? This has to be a negative because I am releasing heat and I need an overall negative number. So when I plug this into my calculator, I get negative 22600 joules. So here I am. This is where I end at my Q2. Now I'm all liquid, I'm going to go down to 10 degrees. So that is Q equals M C sub P delta T. What is my initial temperature? My initial temperature is still 100. My final temperature is 10. So my Q3, MC sub P delta T, where my mass is 10 grams. Okay, my specific heat, I'm a liquid now. So for liquid water, we are going to use 4.18 joules per gram degree Celsius. And our change in temperature, again, we said we started at 100 and I end at 10. So my final temperature is 10 and my initial temperature is 100. So when I plug that into my calculator, I get negative 3762 joules. Now what I'm going to do is I'm simply going to add up all of my values. So my total amount of heat that is released is going to be negative 2222 plus negative 22600 plus negative 3762. And I'm going to put these in a parenthesis so that way we can have an easier visual on our eyes. All right, so when I add up all of these negative values, I end up with a total of negative 28584 joules. Now we want to stick to the rule of 3. So when I stick to the rule of 3, that gives me approximately negative 28600 joules. So it takes approximately 28,600 joules of energy that is released. You can leave it as a negative value. The other way you could write it is this. If you write it as a positive value, you better also have the term released within it. If you write it as a positive value, you better also put in that released, okay? So this word released tells the reader this is in fact a overall negative. So two different ways you can write it. I personally would stick to this way with the negative value, but I do want to show you this because you will see problems where you are told a positive value, but they tell you it is released, so you know that you need to make it a negative value.